Hi, everyone. Really appreciate you all joining us today. We're ready to start here, and we've got a great presentation lined up from TDengine and Casne that'll be covering supercharging data historians for sharing and advanced analytics. And we believe that this will be a new approach to extending data system capabilities for time series data. And before we get started, I just wanted to point out to everyone that you can put your comments and questions in the chat at any time, and that we will also be having a Q&A session after the presentation from Sean and Renner, so stick around. So today we have a couple of fantastic panel members, Sean Ely, our head of product here at TD Engine, and Renner Burkle, our technical program manager at Casne Engineering. And without further ado, let's go ahead and kick things over to Sean to take us away.
Thanks, Chad. So as he said, Sean Ely, head of product at TDengine. If you're not familiar with TDengine, it is an open source time series database purpose-built for IoT. So a little bit more about me. My background is in the energy industry, and I've spent over a decade working with time series data, starting as an integrator working on industrial controls, and later establishing myself as a subject matter expert in emerging technology, innovation, and data science for the energy industry. Renner?
And hey, everybody, this is Renner Burkle. As Chad introduced, I'm one of the technical program managers here at Casne Engineering. Casne is a systems integration and design firm, and I personally spent the last 10 years of my life working with time series data as both an administrator, a user, and an engineer. I've stood up, configured, and managed enterprise systems. I've also designed and built custom data platforms as well. And I'm really excited to join Sean and TDengine today to share some stories that hopefully resonate you with some of your experiences working in this time series world.
So today we've got a number of case studies and kind of use cases of some challenges we've experienced as you try to address the evolving business needs around time series data. And we've got a little bit more about TDengine, some kind of architecture advantages, and finally we'll wrap it up with some Q&A. Okay. So as businesses grow and technology advances, so do the business needs to match this progress. A couple key trends involving business needs that we've observed and we're talking about here today in this webinar around advanced analytics. So kind of every chief digital officer or whatever title that's similar wants to involve kind of AI and industry and kind of build advanced analytics. And there are a lot of companies out there providing these type of solutions. So talk a little bit about our experience in this space, as well as in the, say, energy industry specifically, you tend to have a lot of development by different developers, each with different systems. Maybe there's different OEMs, maybe there's different kind of technology stack. And so you have this big kind of integration of both kind of different development at different times, acquisitions. And so you might want to centralize all that data into a single place for kind of reporting and analytics and dashboards, as well as a need around kind of sharing data. So oftentimes you'll have a need for kind of reporting with regulators, or perhaps it's sharing with a technology partner or someone who's doing kind of an AI solution, or maybe it's sharing with contractors or even sharing internally. So from there, this brings me to the current state of industrial time series data. For historians like the PI system, there's a long history of proven success, and other than complaints about cost, they match the prior business needs very well with their on-prem solution.
All right, so I'll take these next couple slides. So yeah, as Sean mentioned, traditional historians have done well with single sites, but as the needs of the business evolve around us, we're finding some kind of big picture challenges that we run into again and again. So Sean and I are going to take turns. We're going to talk about some of these challenges and tell some stories. And we're choosing these because we do believe these are big picture trends we're seeing across industry. And hopefully by bringing some of these to light, you can realize this may not be something that you're just facing alone. And we're helping to develop solutions around these things. So the first challenge I'm going to talk about is the challenge of alignment with time series data. And this is going to be specifically when using that data for predictive analytics. So this challenge came up during a project I was working on with a global geodata provider client. So this company had offshore assets all over the world, and we at Casne were tasked with designing a global data platform for them. And this platform would be capable of consuming data from all their assets, historizing that data in the cloud in a central location, and then making that data available for their army of data analysts and data scientists. So, I found this to be a really cool project. And this challenge with data alignment, it relates to the weather prediction data we were collecting specifically from offshore helicopter pads. So this was a safety critical use case. The weather out at sea can be very different than the weather on shore, and the weather at sea can also change really fast. One of the first things I learned when I worked on this project was I've been taking weather forecasts for granted, right? I can open up my phone, bring up the Windy app and see about 5 different forecasts, anywhere I click and see what the weather's going to be like. But this is only because there are weather stations everywhere around us on land. And once you get out into the ocean, the only sensors that are available are the ones that you install yourself. And you can't use those onshore, those land-based weather sensors to predict the offshore weather because it's completely different microclimates between the two. So the goal of this use case was to generate local weather forecasts at the offshore helicopter pads, send that data to the cloud, and then use those predictions to determine if it was safe to fly a helicopter out to the site. So if we couldn't create a high quality prediction, then we could be putting somebody's life at risk. So I like to take a little bit of time to talk about the type of sensors we are using for this. So weather sensors are true IoT sensors. They've got onboard calculations, huge array of configuration options that can modify what sort of data comes out of them, and they produce highly homogeneous data. And now when I say homogeneous, I mean the data is delivered as packages, and that the data in each package is mathematically related to each other. So for example, in this weather sensor, pressure is a function of temperature. Humidity is also a function of temperature, and all the wind speeds and directions are all mathematically related too. And it just so happens that this homogeneous and aligned data is already in the format analysts and data scientists need for their models. However, typically, when we would process this data into a historian, we would break apart that message and we would silo each variable in its own tag. And this can cause an issue for your predictive analysis. So when most people hear historian, the first thing they think is timestamp and tags. Each tag is like its own little database, and each tag is processed individually from each other. However, in this project, using this individualistic treatment and siloing data into tags prevented the analysts from creating high-quality predictions. So here's what happened. As I mentioned, the data coming out of the sensors was highly homogeneous, but our historian and data model required each property to be processed as its own tag. So this meant that we needed to write some custom code to break apart the message into its individual properties, process them one by one, and store them in the historian. And one of the greatest considerations in a time series scenario is, where does the timestamp come from? So in this case, the sensor wasn't sending its own timestamp, so we need to provide our own. So we use a GPS clock to attach a timestamp to each message at the point it entered in the historian, right? So we have this big loop in code that's running, and it says, take a property, give it a timestamp, store it in the historian, wait for a success response, move on to the next property, right? And so on, and do the same thing. Well, since we were working through this array one by one, the processing delay started to introduce a time offset between these different tags, even though they all came from the same message. So our data was no longer aligned. Now this offset, it was just on the range of milliseconds to microseconds. If you're just looking at the first couple of decimal points past seconds, you wouldn't have even noticed, you wouldn't have even noticed it. And for cases like trending or monitoring, it really wouldn't have even mattered at all. Now, in general, if you're using historian that stores data in tags, when it comes time to compute forecast or predictions, the first thing your data scientists have to do is try and undo everything you just did to store this data in your beautiful and well-organized historian. Right? They have to realign that data back to the original timestamps and the way that the data was originally grouped and all aligned, because that's the format that their linear algebra and their models need to be in for them to predict anything. So in our case here, once the data analysts got a hand of the data, they started reinterpolating it to get it back on the same timestamps. But the problem was over thousands of messages, those tiny offsets started to add up. Every single one of those offsets was technically a small error. And after computing thousands of messages, their model started to diverge. And that meant the quality of the predictions went down the trash. And what I didn't realize going into this is these forecasts can be so sensitive. So in this case, we got lucky. So we were still in the design phase and we had an easy fix, right? We just rewrote our code to make sure a single timestamp was applied to each message before the message was broken apart. But we were also lucky because we were working directly with the users. So they're able to communicate the demands of their use case directly back to us. And we can incorporate that feedback immediately. Not everybody is going to be this lucky. So I've seen historians filled with decades of data that isn't suitable for predictions. And this is because when these systems were implemented, either the design or the historian technology itself did not anticipate for the future we live in today. And this is a future where prediction has become essential for operation in many, many use cases. So now, we need to design systems with predictions in mind. And that means wherever possible, we need to make sure data alignment is not disrupted during the historization steps. Your data scientists will thank you. Your business will thank you. You might even save somebody's life if it's a safety critical use case like this. All right, so I'm going to pass things back over to Sean, and he's going to talk about data inertia.
Thanks, Renner. So the second data system challenge we'll be talking about is around the inertia of data. This concept revolves around the idea that it can take considerable effort to do useful work with a large amount of data, similar to the physics concept of inertia. A good example of this concept is the process of ETL, extract, transform, and load, which can be very difficult with large volumes of data. From my experience, trying to build advanced analytics is near impossible without first addressing the processes and data engineering needed to bring your data to your analytics, or your analytics to your data. I'd like to share a story with you from my time working at EDF Renewables. EDF is a renewable energy developer, asset owner, and operator focused on grid scale and distributed solar, wind, and storage. While I was working for EDF, I led a data science team focused on asset optimization. Most of the priorities are the projects, like the one I will be talking about today, focused on optimization of wind energy. This project used a handful of measurements from wind turbines, like wind speed, wind direction, and active power, and used these measurements to calculate the optimal direction the wind turbine should be facing relative to the wind direction. So as you'd expect, if you face the wind turbine towards the wind more often, you'll be producing more power. However, the calibration of these sensors, which tell the wind turbine which way it is facing, are typically not very precise, and they can actually shift over time. To develop and deploy our algorithm, we first needed to address the challenge of data inertia. We tried two approaches. First, we tried using EDF's data lake, where they brought data to the analytics. Then we tried bringing the analytics closer to the data with a custom API built off our time series historian. In this story, I'm not projecting on data lakes in general, nor am I commenting on the current state of EDF's data lake, just my personal experiences from 5 years ago. And in my experience, when I tried working with our operational data in our data lake, I ran into some serious challenges. The first challenge I ran into was that the data model used for the data lake, data for every project for a single day was stored in a single table. That was great for daily KPIs, but it wasn't optimized for long-term analyses. So for example, if I wanted 1 year's worth of data for a single project, I would need to perform 365 joins. The second challenge I ran into was in the data format for each table. For each project, while being similar in data format, they were slightly unique in which measurements were provided by the OEM and the SCADA provider. And it was surprisingly challenging to line on a uniform way to map all that project data into a common schema. The end result was a uniform schema which was flexible enough to handle all types of data, but it was difficult to work with, and it was also a bit cryptic. And thus, I had to have my own spreadsheet to translate all of those new labels and project numbers into the names of fields I was used to working with. And another challenge was in the volume of data. Getting all operational data from every project in the world into a single table required some serious ETL. And I often found that data I was looking for was actually missing. So this brings me to our second approach, where we used a custom-built API to pull data into Python for development and deployment. This approach brings the analytics closer to the data and address the issues with data format, cryptic schemas, and missing data. This approach worked very well, and I was very lucky to have been able to take advantage of a very good API that was built by our operational data team. However, this approach also had its own challenges. It was difficult to pull large data volumes I needed for my algorithm. And when I did pull the data, I had to manage my own memory and amount of data I could process at any time. The variables I was using for the analysis were highly dependent and required controlling for the dependent nature. And unfortunately, the data resolution was not nearly as high as I would have liked due to the data volume and processing constraints. So instead of working with, say, something like 1 second raw data, I was working with anywhere between 30 seconds and 10-minute averages. And between the 4 different highly dependent variables, there's something seriously lost in trying to model that relationship with 10-minute averages. And finally, using a REST API didn't solve the challenges around heterogeneous data. So there was still considerable work needed to pre-process the data to make them uniform for an analysis.
All right. Thank you so much for sharing that, Sean. So the final challenge I'm going to be talking about today is sharing data, which I'm sure you all know can be a really big challenge in your organizations. So prior to working as a systems integrator, I worked in pharmaceuticals. And while I was there, I wore many hats, 2 of which were data system administrator and data system user. So this meant I was very intimate with how to obtain the data, find it if it was missing, and then how to use it. Unfortunately, this also meant I was the guy everybody went to if they needed data. Sometimes my entire week was just replying to emails from other sites and doing manual data pulls for them because they didn't have their own connection to our local data system. And now that I look back at it, I realize, okay, they did in fact have a connection to our data system. It was me. I had become the human connector, right? The human cog in the data machine. And I know this has happened to a lot of people. Now, what's crazy to me is that this workflow is widely accepted as normal. But the way I see it, this is more of a symptom of technology failing to adapt to our increasingly distributed and interconnected world. So in my case, the drug product site would email me at the drug substance site where we made the chemicals and ask for outgoing quality attribute data compared with their incoming data, right? So this data should always match. And we had the same historians at each site, but I still had to export the data manually to Excel, email it to them, and they would continue using it in Excel. So they took all of the cross-site usage outside of the enterprise historian and put it into a completely manual workflow. This also meant that they couldn't use any of the client tools provided by the historian because they were just, in Excel and had to make everything manually. So not only does removing data from the system of record open up the opportunity for human error, or God forbid, someone manipulating the data, it also significantly slows down your experts, right? I couldn't focus on my actual deliverables because I had become a full-time human cog. The last thing I want to mention is that sharing data within your site can be just as complicated as sharing data outside of your site. But as you know, sometimes when sharing data outside, it's more of a good to have, or someone's doing an ad hoc request. Sometimes sharing data within your site is required from a purely operational standpoint. Many times it's required between machines for the equipment to function, or somebody needs that to make processing decisions in real time. So implementing this data sharing within a site using best practice methods can be incredibly complex. And that's because at the end of the day, we need to protect our data sources from cyber attacks, and any openings between different networks and systems is a potential vector for attack. So this has led to the rise of the Purdue model. It's something that continues to gain significance, notoriety year after year. And the Purdue model is the best practice way to safely share data from critical security zones like manufacturing networks with your business networks, or where your people and consumers are. In my experience, the Purdue model does not scale well in terms of complexity. And this is because as you increase the number of data sources you want to share and increase the available audience, the more potential risk you start to accumulate. So then you need to add additional security hardware and make your networks even more complex. But then that added complexity itself starts to constitute its own security risk, which is what you're trying to avoid in the first place. So very quickly, you can get caught in this feedback loop and be stuck in a losing battle against entropy. So the pharmaceutical company I worked for, they did actually try to formalize a way and make their own way to share data between sites and share this OT data from the actual manufacturing floor. So they spent hundreds of thousands of dollars and multiple years on this global project. They flew SMEs all around the world, and they built a custom framework on top of their historians. But in the end, the project failed. So it failed because in the end, they had a system no one was willing to or capable of maintaining. All the infrastructure under the hood to make that data sharing possible was so complicated that they knew that they could never validate the system. And since it wasn't validated, and this was a GMP environment, every data point in it had to be manually verified by hand before the data could actually be used for anything. So, at that point, the entire purpose of the system had been defeated, because even if you wanted to use data from another site, you still had to email the local SME and have them go verify the data manually just so you could use it. And often that process, because not only did they have to check the data, they had to then go into this other online system and manually show that it had been checked. It ended up taking longer than if they just emailed you, the original Excel file that you had asked for before they even implemented this project. So at the end of the day, they were completely back to square one because data sharing was so difficult with their historian infrastructure.
So given the technology challenges we faced, both Renner and I independently had an aha moment where we realized that there's a better way to architect time series data, and thus we were drawn to a solution provided by TDengine. So we have two case studies to illustrate how this new approach can address some of the challenges identified as part of the evolving business needs.
All right, so I'm going to talk about the first case study. And this first one we're going to talk about today is a joint project between TDengine and Casne Engineering. And this project, was a direct result of following after the business need to enable advanced analytics, in this case using ultra high-speed data. And when I say high speed, I don't mean a couple data points per second. I'm talking about tens of thousands of data points per second per sensor. So earlier this year, Casne worked with TDengine to develop a predictive analytics platform for a company who makes car parts by using hydraulic presses to bend sheets of steel. They wanted us to design a system that uses vibration data from their hydraulic presses to predict motor failures, because these failures were costing them hundreds of thousands of dollars a year. Now, the gotcha for this project is that their entire process of bending metal only takes 1.2 seconds. So that means we only have those 1.2 seconds to build our entire prediction model. And I'm sure you could figure out, if we're only capturing, a couple of sensor readings per second, we're just going to end up analyzing pure noise and be lucky just to have, a handful of readings to try to build that model. And really, we wouldn't find anything meaningful out of it. And this is actually what happened to the company before. They tried to execute on this use case and they failed because they could not analyze and capture the amount of data required to bring about a meaningful prediction from their data. So how much data do we need to collect? Well, it adds up really quick. So each vibration sensor can report 20 kilohertz data, which is 20,000 data points a second. And we designed each motor to have 2 sensors per motor. Each press has 7 motors. So you can do the math, 2 sensors times 20,000 data points a second times 7 motors per press. That's nearly 300,000 data points just for a single press, 300,000 data points per second, that is. And there are dozens of these presses at the factory. So very quickly, we enter into millions of points per second territory. So one of the things that made this architecture interesting is that for this stage of the project, the client wasn't interested in storing the raw data from the sensors. They only wanted the prediction data. So the classic approach would be to collect your data, store it, and then analyze it. But in this case, we needed to think of this as a streaming data application and design with the historian at the end instead of in the beginning. And that's just the type of architecture that we ended up designing with TDengine. So we came up with a microservice approach in which data is collected from the sensors, converted from analog to digital readings, then read directly into the AI ML engine. This engine creates a prediction model that updates with every data point it processes. So you have a one-to-one pass-through in terms of data volume going through that engine. So those hundreds of thousands or millions of data points per second coming through come out as hundreds of thousands to millions of unique predictions. So the historian that we needed to choose for this, it needed to be capable of handling these really high rates of data. TDengine was a great fit, and in our architecture, TDengine captures all the outgoing prediction data and it stores it. So the client can not only check at any moment in time if their assets are close to failing, but they can also observe how the possibility of failure has changed over time. So before I hand things back over to Sean, I just want to say, we had an absolute blast in this project, getting to use all the latest technologies in a use case that probably wasn't possible a couple of years ago. And the best part for me is that this architecture we came up with is going to be highly reusable. I can easily see this being used across different industries and different projects. And, that always makes for a successful architecture from our point of view.
So as businesses grow and have multiple project locations, and as technology enables the remote monitoring of multiple sites, the business needs to consolidate operations into one or a couple operation centers with a centralized data store emerges. Consolidation projects are often an effort in human resources, process and change management, physical design and layout, and the digital centralization of data and software. In the next case study, we will show an example of how TDengine was able to centralize data and enable data sharing in the automation of normally tedious data collection processes. This case study involves a power generation operator which operates a mix of natural gas and coal plants in North America. They operate 4 portfolios with a total of 32 power plants. The company had a problem with 4 separate portfolios of power generation assets. They had 4 entirely separate systems with 4 different VPNs used to access 4 different monitoring dashboards and collect data from 32 individual historians. To view the current status of all their assets at the same time, they used 4 separate machines, each logged into a separate VPN to view that portfolio's dashboard. They were looking for a way to centralize their data for easier monitoring. And as a secondary objective for this company was to share data from their operations for business purposes. In their old process, to achieve this, an analyst would log into each of the 4 VPNs and use Excel to pull data from each of the 32 historians. This data would be manipulated in Excel and then be saved off as a CSV file. Each of these CSV files would then be manually uploaded to a cloud database for reports and dashboards. This process was executed regularly, and it made the analyst the human cog in the data machine. So let me take you through how we solve these challenges with TDengine. So since there's 4 different portfolios, depending on the owner and the portfolio architecture, either a single TDengine connector was installed in their business network, or perhaps multiple connectors for each power generation site. The connectors in this design are sitting upstream of their existing data historian and are pulling a subset of data for dashboard and reporting. Each connector has a single outbound connection over HTTPS. And in terms of architecture, this could be from the control network to a centralized on-prem instance of TDengine in the business network, or in this specific case, it is actually from the different business networks to a cloud instance of TDengine. And here we show the full architecture with data centralized in TDengine hosted in AWS. Once the data is centralized, data can either be shared or consumed through data analytics or visualization tools. For this case study, the company is using Grafana to create a single dashboard of all 32 plants. And they're sharing data with their cloud consultant, who's using a Lambda function to write data to their cloud database for business reporting and dashboards. This Lambda function combined with TDengine's REST API, automates the business process that used to have an analyst manually generating CSV files from each site for upload. So I'm going to take this opportunity to provide a bit more detail on the architecture outlined in this case study. In the next 3 slides, I'll break out some of the capabilities around data centralization, data sharing, and advanced analytics. To centralize data, there are numerous ways to get data into TDengine, such as our REST API and SQL insert statements. However, the easiest way is to use one of our connectors, which connect to the Pi system, OPC UA, OPC DA, MQTT, and Kafka. And they have built-in data cleansing and transformation tools. To share data, you have the ability to share the entire database, a subset of the database, or even aggregated or transformed data. You can accomplish this through flexible SQL queries to define the data sharing. And data sharing is secure with token authorization and the ability to set expiration times. TDengine also has real-time stream processing, which uses SQL with some time series extensions to analyze and transform the data. And for more advanced analytics, data is easy to ingest into Python or other programming languages, or use with one of the integrations with third-party tools. So let's dive into a couple comparative advantages of TDengine compared to some similar solutions. TDengine recently did a benchmarking test based on the industry standard time series benchmarking suite. And TDengine outperformed its competitors by an order of magnitude. In terms of ingestion, TDengine was up to 10 times faster than InfluxDB. And in terms of query performance, TDengine was a staggering 37 times faster than Influx. I also want to mention that TDengine is fully open source. So as an open source database, it's very popular. It has over 21,000 stars on GitHub and over 270,000 running instances in over 50 countries. In addition to the open source community edition, TDengine also has an enterprise edition with additional features like security, backup, and industrial interfaces. And a fully managed cloud service on Azure, AWS, and Google Cloud. Feel free to go to our website to read some more about the details or do a free trial. No credit cards required. And since everyone always asks about pricing when you're introducing a product, we have affordable and transparent pricing. We've adopted a fixed price model that doesn't scale linearly with the number of metrics. So that means since TDengine is purpose-built for IoT and built for massive amounts of data, it's priced accordingly. So if you double the size of your metrics or the number of tags, it doesn't double the cost. You can kind of see an estimation here as the size grows. And you can also see our pricing on our website.
Great. Thank you, Sean. Thank you, Renner, for the presentation today. We're going to turn it over to the question and answers. We had some great questions up in the chat, and we're going to go ahead and answer some of those right now. So our first question, let's see if we can get this on the screen. Different sites use different tags. What's the easiest way to correct these if I want to consolidate my data? So I'll let the panel take this question at this time.
Yeah, I'll jump in and answer that. So I think there's the question asked, and then there's also kind of a slightly better or a different question that I've experienced as well. The question asked, there is ways to kind of transform and add, say, like prefixes to your tag naming. But more often, when you're consolidating data into a database from many different locations, what you experience is that tag naming or metric naming, it tends to not be unique. So if you have a plant A and a plant B, they might both have like engine 1 or sensor, temperature sensor 1 or something like that. And so you tend to have duplicate names across different projects. And so kind of our approach to this problem is to add kind of prefixes to your naming, your table naming convention. So you can prefix what the project or plant name is. That way you have unique naming convention and you can consolidate everything together.
Great. Thank you, Sean. Renner, anything to add there? Or?
No, Sean's answer was great.
Excellent. Great. Our next question comes from Cigar. I'm going to go ahead and display here and maybe rephrase it. So I think the question here is, PiVision seems to have a screen that's less appealing when it comes to comparing it to other tools like Power BI and Tableau. Why is that?
I love this question. I know exactly where you're coming from. And I think, the good news is, right, that I'm saying, from kind of my point of view as a system integrator, working with many vendors, more and more visualization, especially industrial visualization options are coming out. And these are things that work into your existing system architectures. Specifically, why is there kind of this delta between PiVision and some other visualization tools? I think it's just a matter of frequency of updates. I think, frankly, some other tools are being updated far more often, and it tends to reflect in the type of visualizations that you can make with them.
Renner? And Cigar, and anyone else here in the chat, there are follow-up questions to what we're discussing. Feel free to put those in the chat as well. We're going to move on to our next question with Jonathan here. The question is, how does TDengine collect data from standard end devices like Allen Bradley PLC or Modbus type devices? Do you have native drivers to accomplish this?
Yeah, I'll answer that one. So right now we have a handful of native kind of drivers that we've kind of mentioned, some interfaces around MQTT and OPC, UA and DA. In terms of kind of the full, there's a lot of different industrial protocols and a lot of different providers. One of our focus and kind of on our roadmap is to provide more solutions for this space. But we also kind of, in the meantime, we don't have a native driver for Allen Bradley PLC or Modbus, but we do have connections to things like Telegraph. And so you can use Telegraph to read data from those, and we can consume it directly from there. Or there's a number of other kind of interfaces we have to open source tools to read from those. those type of data sources.
Cool. Thank you, Sean. Great. And our next question. So it states, my timestamp increments, example, 15 seconds, 1 minute, vary by site and device. What's the easiest way to align them?
Jump in and answer that one as well. So there's a number of ways to align. So TDengine's built with standard SQL, and then we have custom built time series extensions that add to kind of the SQL language, especially for this type of scenario. And so you can either do aggregates. So we call them windowed queries, in which you aggregate those timestamps. So if you wanted to, say, aggregate them up to a minute, or if you wanted to aggregate them up to an hour or a day to align the timestamps, depending on your use case, you can do those with our kind of windowed queries for aggregates. Conversely, if you wanted to kind of downsample the minute timestamp to every 15 seconds, we've got interpolation. So you can interpolate that every minute into, say, 4 data points, so every 15 seconds.
Got it. Thank you, Sean. And our question from Gabriel. When using the connector for OPC, UA, and Pi, are you simply getting the tags, data, or the asset modeling, AF for Pi, data model for OPC, UA, in TDengine?
The way that I'm kind of interpreting this one is, for example, with the Pi connector, are you reading tag data, or you can also read element data, and then say you could, have an entire AF element with all the different attributes in there. So kind of, where does the connector source data from?
Thank you, Renner. So for the Pi connector, we have 2 modes. We can both pull directly from Pi tags and get that data into TDengine, as well as from AF and AF elements. And so for that, we actually map the element based off the element template. So basically all the attributes with Pi tags become columns in a single TDengine table, and we align those all together. And then we're also pulling in the static attributes as tags into TDengine as well. So we're kind of mapping a little bit more than just the time series data.
Yeah, that kind of brings up one of the interesting differences between TDengine and say a historian, tag using historian like Pi, where I had mentioned earlier a lot of stuff about siloing data, but in TDengine, you have this concept of a super table where you can have multiple properties. So it'd be like if you were, instead of having a separate tag for pressure, temperature, volume, whatever, you have those all in one tag or super table.
Yeah, absolutely. So TDengine takes a 1 table per device approach, which makes a lot of sense for kind of IoT use cases, because you tend to have a number of metrics for a particular sensor or for a particular kind of logical unit. So saying like an engine that have all these kind of related quantities to them, you'd put them in a single table. And by storing them all together, there's a lot of benefits in terms of performance, in terms of storage size, and it makes it easier to kind of work with that data, having it all aligned together. And as Renner, as you mentioned, if you have a 1 table per device type approach, you're going to end up with a lot of tables. And so to kind of address this challenge, we came up with the super table, which is essentially a template. And it doesn't store any data, but it stores the schema for those tables, and can also be used, and also has some kind of metadata associated with it. So we call them tags, but with SCADA systems and Pi, tags are a little bit ambiguous. So you could also just call them, say, labels. So we have the labels associated with the super table, and you can use that super table to query all kind of similar devices. So everything with the same schema at the same time. So it makes it much easier for kind of like aggregating and working with large volumes of data, and also having a standard approach to that data model.
Well, great question there. Thank you to the panel for answering that. And our last question is once again from Sagar, a little bit of a side spinner here. In your opinion, how could the pharma industry get the most out of TDengine?
Renner, do you want to take a crack at that?
Yeah, I mean, I think it's a good question. I mean, I think at some level, TDengine is a historian. So, at kind of the base level, the question can be interpreted as, how does pharma industry get the most out of a historian? Which I know there's decades of proven use cases for having one. I guess for things that would be TDengine specific, that maybe would be TDengine versus a different historian. I'd defer that to you, Sean, and let you talk on that.
Yeah. I would say my background's more in the energy industry, so I would have to, we'd have to talk specifics of the use case, in which case I could talk through it. But I don't have anything on top of mind in terms of specific pharma use cases.
I would say, something that kind of comes to my head is, especially in places where there is a lot of modeling going on. So at your, small scale, research, process design stage, it could be very useful to make use of those super tables and also then share that data, to other facilities very, very quickly. And I've, in working with different pharma companies, I've noticed that sometimes they're reluctant to have a separate historian. For example, speaking in terms of like a pie system, I've seen people be reluctant to have another pie system for their small scale stuff, just out of like implementation costs and reasons and stuff like that. And so, yeah, I think that TDengine would fit really well there. There's no reason that it couldn't also, be your main plant historian as well. But I think specifically that would be a good use case, for it, especially in existing companies.
Cool. Thank you, you guys. And last question here from Douglas, and I actually really like this question. I'm curious to see what the panel has to say about this. Is TDengine a historian?
I say yes, but I'll let Sean. Sean's had a product. It's his product. I'll let him answer.
Yeah, I mean, TDengine is a time series database. I'd say yes, it is a historian. Renner, am I missing anything from the definition of a historian versus a time series database?
If you are, I'm missing it too. Okay. So from my,
yes, it is.
From my world, we tend to use the words interchangeably. There may be some sticklers on diction out there, but
I think the overall answer is yes, but the back end of that is, we want to talk to you about that, right? If you have an idea for a historian type use case and you like what you saw today, we'd like to speak to you more about that and see what you're thinking, see if TDengine provides value there in place of a historian. So absolutely. Great. Well, before we close things up here, again, as Sean mentioned, as the team has mentioned here, TDengine is a very powerful open source database. And open source means that you get to use it for free. So there's a few different ways you can try it. If you like what you saw today, you can register for our cloud service at tdengine.com. You can also download our package or container image from tdengine.com, install it on your own machine, or you can download the source code from GitHub and build it yourself. There's a ton of forks of TDengine out there. So we encourage you to get involved with our community and be involved and provide your feedback about our database there. And really, thank you to everyone here. Thank you to the panel for your time. Thank you to everyone who joined us today. Feel free to follow up with us directly if you have additional questions or you'd like to talk to us about something specific that you found interesting today.